Hello, my dear students, and welcome back to the second part with this DC-DC converter chapter. Let me start sharing my screen and continue with our chapter. So I think you can now see my presentation slides, and we can now start with our pointer. Okay, so in the previous part of this chapter, my dear students, we have recognized together what's called the buck converter. And we have studied the main architecture or circuit schematic for a buck conversion. A buck conversion means simply to buck or to reduce or to step down your output voltage with respect to the input voltage. And we reach a mathematical formula that governs this relations, saying that the output voltage is equals to D times the input voltage, where D here represents the duty cycle, or simply the raising time of your driving signal with respect to the complete period. As you can see, by default, this duty cycle is a number smaller than or equal to 1, which means that this output voltage will be stepped down with respect to the input voltage. And as a part of our power balance equation, what we are going to reduce in the voltage, we have to gain in the current, as you can see from this equation. So if you are bucking your voltage, that means simply you are boosting your current with the same factor D. Now, what we are going to consider is the other process, which is the boosting of your voltage. So the target of this section is to study together a schematic that is capable of boosting the output voltage. I mean, stepping up the output voltage with respect to the input voltage. So let's start together considering this schematic. Again, we are going to apply the same procedure of analyzing the circuit with the same concepts we have learned in part number 1. So as the first step, what we are going to do is we are going to monitor 3 or 4 important signals in this circuit. The driving signal, which is simply this voltage coming from the pulse width modulator to drive the gate of your transistor, knowing that this transistor is acting as a switch. So whenever the signal is high, the transistor will be a short circuit. Whenever the signal is low, your transistor will be a open circuit, ideally speaking, of course. Then we are going to also monitor the current flowing into a coil, which is IL, the current flowing in the switch, which is IS, the current flowing into the diode, which is ID. Okay, so let's start first assuming that we have a high signal coming to the switch, which means that this switch will act as a short circuit. Automatically, your circuit will be reduced to act like just a VG or a generator connected in series with a coil and then a short circuit, which is a switch, of course. Concerning signal monitoring, then we have a high signal coming to the driving signal of your MOSFET. And next is the current flowing in your coil is going to increase because now coil is charging. And as you can see, the current flowing in the coil is typically the same as the current flowing in the switch. So it's short circuit. That's why IL and SI are identical. And of course, there is no current flowing in the diode due to the short circuit, so there's no current here. Alternatively, when the driving signal coming to the MOSFET is low, that means that this is an open circuit. So what's happened is that your circuit would look like that. So here you have a coil, and then you have a capacitor, and you have your load. So let's again monitor the voltage here and there. So as you can see, when this is low, now the current in the coil will start to discharge. So that's why the current here will go lower. And then what's happened also, there is no current flowing in the switch. The current flowing in the switch is 0 because the switch is open circuit. And the current flowing in the diode is typically the same as the current flowing in the coil. That's why this is identical with them. Again, this will be repeated when the switch is turned on and then turned off. And if you remember, this is typically the same procedure as we did for our buck converter. Now, you can apply Faraday's law to determine the current in terms of voltage and time, knowing that V equal LdI by dt. So you can use this in order to make this equation. For example, here, the voltage applied in the red portion of the graph is typically VG, because now let me return now. Now, as you can see, the voltage on the coil is typically VG. So as you can see, VG equal, or the voltage on the coil equals to VG. So again, here, let's go to the equation. So I equal VG with the time duration, which is dt, over L, which is the inductance. So this is the equation you can use to determine the current, or the incremental current, let me say, flowing in your coil. Now, back to the analysis. First of all, you can say that the current flowing in the capacitor, or the average current flowing in the capacitor, is equal to 0. This is, we already have considered in our previous part, when we consider the main functionality or the main concepts related to the power balance and the current flowing in a capacitor and voltage drop on an inductor and so on. Now, using this area equivalent, if you remember, in the positive portion of a signal, you have a voltage applied to the coil equal VG, as you, let me show it to you again. So here, the voltage on the coil is equally to VG. So in the positive portion of the signal, the applied voltage on the coil is VG. While in the negative portion, I mean, when the switch is off, the voltage applied in the coil is simply VG minus V output, because if we make a KVL here, we will get VG equals V coil, or the voltage applied on the coil, VL, let's make it, plus V output. So V coil, or the voltage applied on the coil, VL, equal VG minus V output, which you will find it here, as you can see here. So in the red portion, it's VG. In the blue portion, it's VG minus V output. So the red area will be simply VG times dt, as you can see here. Sorry, VG times dt. While the blue area will be V output minus VG times 1 minus dt. So simply speaking, you can consider that, or you can cancel T with T, getting that V output equal VG over 1 minus D. Knowing that D is by default smaller than 1, so you can know now that the output voltage is definitely greater than the input voltage. And that's why we have a boosting effect here for the voltage. Let's consider the current. So let's consider the current flowing in this node. Typically, the current flowing in this node is equals to the current coming into the node, which is ID, minus, or yes, the current flowing in the capacitor minus the current flowing in the load, should be equals to 0. We have one ingoing current, which is ID, and two outgoing currents, which is IC and I output, as you can see. And as you already know that the average current flowing in a capacitor is equals to 0, that means that the current in a diode is equal to the current in the load. And if you recognize that the current in the diode is typically the same as the current in the coil, is typically the same as IG. And the current in the output node, I output, is the output over RL, obviously. That will lead to the fact that IG, which is the source current, equals to I output over 1 minus D, which is simply extracted when you substitute by V output with VG over V output equal VG over 1 minus D. That gets that IG equal I output over IG equal I output over 1 minus D. So again, you have boosted your voltage with a factor 1 minus D, and you have bucked your current with the same factor 1 minus D. So again, a power balance occurs in this case. Okay, so this is again a summary for all the equation for a boost converter. Let's now turn to a third case, which may be the most commonly case used, which is a buck boost converter. This is another topology. So we are just, as you can see, we are just rechanging the position of the switch, the coil, and the diode. That's all. Let's see now, or let's do now the same procedure we did for the previous two cases, considering the current flowing in the coil, the current flowing in the switch, the current flowing in the diode, and the driving signal, of course. So, as you can see, when you have a high signal here, which leads to a short circuit here, you will end up with something like that. This is simply because this diode will be in a reverse bias, making this as an open circuit. So you simply disconnect all these portions of the circuit, leaving only a VG and a coil, which is quite the same as what we did with a boost converter, if you remember. So here the voltage in the coil is typically equal to the voltage of the generator or VG. Let's now address the signals. So as you can see, it's typically the same as in the boost converter. When your gate signal is high, the current flowing in the switch and the current flowing in the coil are identical, and no current flowing in the diode because simply the diode is a reverse bias. Now, what happens if this is an open circuit? So you disconnect the source now, and what you will get is something like that. The source, your generator is no longer attached to the circuit. The current is flowing from the coil, and or the current is charging from the coil to the load and returning back. So the current flowing now will be in this direction, making this as a short circuit or as a forward bias, and this will be the polarity of your capacitor, as you can see. So what about the current now? Now, as you will see, your driving signal is low. Your coil will start to discharge its current in the circuit, as you can see. And then your switch, of course, is off. So this is 0. And again, the current flowing in the diode will be typically the same as the current flowing in the coil, which is in the blue. And again, we are going to repeat the same process once more again. Because before doing Faraday's law, we have just to recognize the voltage applied to the coil. So as you can see here, that the voltage applied to the coil is typically the same as V output. It's a parallel branches of V coil, V capacitor, and the output. So this is typically the same. So when you are going to apply here, you can say that if you applied on, again, the red portion, you will say that in this case, the voltage is VG, as you can see here. The time is dt, and this is R. So this is similarly the same equation we get in case of a boost converter. Let's go to the nodal analysis. Again, the current flowing in a capacitor is equal to 0 in average, and let's do a balance equation. Now this is your balance equation. In the red portion, the voltage applied to a coil is VG. So it's VG times dt. In the blue portion, the voltage applied to a coil is V output. So it's 1 minus D times T times V output, as you can see. And this equals to 0. Equalizing this equation, you get that V output equals VG times D over 1 minus D, which is actually a very, very interesting equation. Why? Because in this equation, if you substitute with D smaller than half, you will end up with a factor, which is D over 1 minus D, smaller than 1. So if D is smaller than half, your circuit will behave like a buck converter. If D is greater than half, then your circuit will behave as a boost converter, because simply this ratio, which is D over 1 minus D, will tend to a number greater than 1. Of course, at D equal typically half, there is no buck or boosting conversion. As you can see, when D equals to half, it's half over half equals to 1, which is V output equal VG. So it's a typical input-output relationship without any conversion, either stepping up or stepping down. So this is another factor. So let's come to that KVL and KCL analysis. As you can see, ID, or the current flowing in a diode, or the output current now plus the current flowing in capacitor equal to the current flowing in a diode, because now the diode is reversed. So ID minus IC minus I output is equals to 0. Again, the current flowing in a capacitor is in average is 0, making that ID equal I output, and this I output equals to V output over RL, and this ID equal IL times 1 minus D, leading to the power balance equation that I output equal D over 1 minus D, IG equal D times 1 minus D times the I output, which is again the balance power equation. When you increase a voltage by a factor, you have to decrease the current by the other factor and vice versa. So what you gain in terms of voltage, you lose in terms of current and vice versa. This is the most famous architecture for a buck boost converter. So this is again a summary for all the equations we have recognized as usual. And let's now see a macroscopic view for the three converters. The buck converter, which is stepping up a voltage with a factor D, a boost converter, which is stepping up, buck stepping down the voltage with a factor D, a boost converter, which is stepping up a voltage in a factor 1 over 1 minus D, and finally a buck boost converter, which can either buck or boost depending on the duty cycle or D. That's why the duty cycle presents a very, very critical parameter in the design of a DC-DC converter. And as you see from the circuits, it's only the play with the position, where to put the coil, where to put the switch, where to put the diode. Based on the position of these three elements, you would totally change the functionality of your circuit. That's why we have all the time we have a generator on the left hand side, and we have a capacitor and the load on the right hand side, but it's only playing with the position. This is the inductor is an energy buffer to convert two voltage sources, as we mentioned. You buffer or you store the energy in one cycle, and then you discharge this energy in the low cycle, depending on your on and off of a MOSFET. So in the next portion of the chapter, we are going to continue with different architectures, as well as different concepts related to DC-DC converters. I would say that what we have passed through in part number 1 and part number 2 is the basic fundamental concepts related to DC-DC converter, considering buck boost and buck boost converters. In the next, we are going to have more and more advanced concepts. And also, it's very important to know, to highlight that what we are presenting here is what we can call the fundamental architecture for a DC-DC converter. However, if you pick up literature, if you Google and search for papers for that, you will find an endless number of other topologies to perform the same function. And herein, there will be a very challenging trade-off between various parameters to evaluate DC-DC converter. Maybe by the end of the lecture, we will consider this, or maybe in another course, we will consider this. And also there is another family of DC-DC converters named by what's called an inductor-less DC-DC converters, whenever you are going to scale up, or to scale down your DC-DC converter to the CMOS level. I will terminate part number 2 by this part, or by this slide, and looking forward to see you in the next part of this chapter, more toward DC-DC converter. Thank you very much.